All right, so we ended the last time talking about how the potential of a cell is related to concentration. And so today we're going to take this equation from down here at the bottom that we were looking at, and we're going to utilize that to do a problem and introduce a new type of cell. So the new type of cell that we're going to look at is what's called a concentration cell. Now, any type of cell is dependent upon the concentration of the products and the reactants, but we can write out a chemical reaction in any given direction and look at determine the potential of that cell. But what's interesting is in a concentration cell, you have this other thing at play is, well, when you look at two reactants that are different, you're relying on which one of them really wants the electrons more than the other. But in a concentration cell, you can often have, right, the reactants and products that are the same. Now, how might this look in terms of a cell? So we could actually draw out a galvanic cell for this. Right, so you could have your compartments, right? So we'll have the anode compartment over here with your anode, right? Where that anode here is zinc solid, right? There's your anode half cell. Of course, that's you've got your cathode compartment as well, with your cathode, which is also zinc in this case. Dissolved in the solution, we would have zinc 2+ for both of them. And here, we would have the connection to them. You could have either a voltmeter or whatnot, right, to measure this. Or if you want to push a reaction in one direction for another, you might use a power source. We'll talk about that power source a little bit later today. All right, don't forget your salt bridge connecting the two. All right, so that didn't work. All right, so you'd have anions and cations, depending upon what those cations and anions are. So this is your typical setup here, right? You'd have, you still have the two half cells that are connected by the salt bridge and a wire. But in this case now, we don't know which of the two solutions is which if we're putting this together as cathode and anode. We have to determine which one is being oxidized and which one is being reduced. And so if we were to take the reaction up top and actually split this reaction into two half reactions, well, we'd have to figure out what was going on in order to determine which direction that reaction was going, for example. But we have two reactions that are occurring. One of them is zinc 2+ that's aqueous. Okay, I'm not going to put my concentration in there yet because we haven't determined which one is which. And so in this case, we're talking about the zinc 2+ aqueous plus 2 electrons reacting to form zinc solid, right? And that's the reduction that's occurring. And the other one being zinc solid that's reacting to give zinc 2+ plus 2 electrons. Okay, let me put in, we don't know which of these two zinc aqueous solutions is which at the moment. But we can determine that fairly easily here, but this is the two half reactions. So one of these half reactions is occurring in one cell and the other half reaction is occurring in the other cell, assuming this is a galvanic cell. So what we can do first off is say, well, this first equation, right, that's the reduction, and the second equation is an oxidation. So we know that the second equation is for the galvanic cell on the left, because that's the oxidation that occurs in the anode compartment. And the first equation is the one that occurs on the right, because we know that's where the reduction takes place based on our drawings in the past. Because we have electrons, as usual, going from left to right through this wire. And you can draw it the other way, but we tend to draw out these cell diagrams in this direction, okay? So the next question here is based on the concentrations. Which direction will this reaction go? And so for this particular reaction, what you can do is say, okay, well, I've got two solutions here. What's going to be driving this chemical reaction is the fact that the concentrations of the dissolved solutes are non-zero and they're not equal. And so what's going to wind up happening is that a reaction is going to proceed in the direction that will eventually make both concentrations equal. Okay, and so that's a key here. And so in order to make both of these concentrations equal, this chemical reaction is actually going to have to go in the reverse, at least as written, okay? And so we can look at this from the standpoint of our chemical, or the equation for the potential for the cell, where we have the potential of the cell is going to equal the standard reduction potential of the cell minus 0.0591 over N times log of Q. So in this particular reaction, you notice that we have a reaction that's going in the opposite direction of what we would consider to be the spontaneous forward reaction. So something is actually going to be forced to drive this reaction in the reverse, okay? And so we would have to have a power source for that. And that's something we'll look at when we talk more about electrochemical cells. But we could actually, if we were just to hook up a voltmeter here, right, and we hook it up in the correct direction, right, the only thing that would switch if we just hook up a voltmeter is the sign of the reaction, right? Anytime we have a spontaneous reaction as written, right, the sign of the cell potential will be positive. If it's a negative, then either our leads are connected backwards or the reaction is going in the opposite direction of what we think. But here, what we notice is if this chemical reaction is actually going from right to left, then we know that the solution on the right has got to be the one that is less concentrated, right? Because what's happening here, remember at the anode, the zinc is dissolving. The zinc solid dissolves to make zinc 2+. So on the left, we should have our 1 molar zinc solution. And on the right, we should have our 2 molar zinc solution, because this zinc is going to form more solid, whereas the zinc on the left in the anode is going to form more of the aqueous zinc, okay? So that's how the direction of this reaction actually goes, is the electrons are moving from left to right as the concentration of the solution on the left goes up and the concentration of the solution on the right goes down. And then we can go and take that particular chemical reaction, and if we're looking at it from the standpoint of the chemical reaction as written, what we need to do is write in our Q and understand what our Q is. So Q is going to equal, well, based on how this is written, it's going to be this concentration of the zinc 2+ on the 2 molar side, because that's the product side. Wait, hold on, that's not, yeah, that's the product side as written, divided by the concentration of zinc 2+ on the reactant side, which is the 1 molar zinc 2+. So that's as this reaction is written, okay? And so in other words, Q, right, will equal 2 over 1, okay? 2 molar over 1 molar. Okay, so we're going to take that information, and so we know that Q is equal to 2 over 1. We know that our cell potential will equal the standard cell potential minus 0.0591 over N log of Q. And I want to go back here and point out to you, notice that the number of electrons that are being gained is equal to the number of electrons that are being lost. So that tells you, based on that information, N is equal to 2. And so we can put that down as one of the things we need to have as well. The other thing, so we've got our N figured out, we've got our Q figured out. The other thing we need in order to figure out the cell potential for this concentration cell is, what is this E naught? And that's actually a fairly straightforward calculation, right? What we need for the E naught of the cell is we need to know what the half cell potential is. So in this case, E naught of zinc, okay? And remember, that's a half reaction. Okay, so for zinc, it's negative 0.76 volts if you went back and looked it up in a table. That's what you'd get for the standard reduction potential of zinc. So we know, okay, so the standard cell potential for the whole cell is going to be equal to the half cell potential at the cathode minus the half cell potential at the anode, right, which will just be negative 0.76 because our reduction is occurring at the cathode, minus, well, it's the same standard reduction potential that's occurring at the anode, so minus a negative 0.76 volts. So anytime, you can see that it comes out to 0. Anytime you have a concentration cell, which we tend to think of a concentration cell as the reactants and products, or rather both half cells contain the same types of compound or the same chemical ions, etc. It's just that they're different concentrations. So your E naught for the cell, right? The overall cell potential or standard cell potential would be 0. Thus, the only thing that this cell is that you're taking into account in a cell like this is going to be negative 0.0591 over, in this case, N2, which is 2, okay, times log of Q, which is, in this case, 2 over 1. So it's only dependent upon the actual concentrations. It's not dependent upon what you have in the cell itself. Well, concentrations and the number of electrons that change place. And so you could just plug this in, do some math. You get negative 0.02955 times log of 2, which is 0.301. And so that's going to be, if you just do that math, negative, my eraser out, 0.00887 volts. So this is a very small voltage for this cell, but that would be based on the concentrations given, that would be the standard potential of the cell, which also tells you, if it's a negative, it tells you that it's running spontaneously in the reverse direction. Okay, but if we go back up here, you'll notice that just thinking about the concentrations, right? We have a 1 molar solution and a 2 molar solution. The farther that those concentrations are apart, just based on this chemical equation where we have Q, the farther that those are apart, the larger the value for log of Q becomes, right? Or the smaller, the more negative or the more positive that becomes. And so the that Q is really the important thing here is, well, the more the bigger the concentration difference, the bigger the current that's going to run through that wire and give you that certain potential. You'll have a higher potential, basically, right? And so that's what you have with a concentration cell. Is the idea is now it's based on the concentration of the products and the reactants, where the products and reactants just happen to be coming from the same chemical reaction. But remember, they're isolated in two different cells that are separated from each other, and that's how we are able to harness this reaction to get those electrons to flow to eventually do some sort of electrical work with those electrons as they flow. Okay, and so the idea now is we can have these, so we have these concentration cells that can generate energy for us, and that can be useful, but of more use in general is sort of an application of electrochemical reactions, and that's batteries, okay? So really what batteries are, okay? Batteries are just a way of using chemical energy, right? And that chemical energy is stored in the actual products and reactants, really in the reactants that we can think of, right? And we're going to use that chemical energy to do electrical work. And we're doing it, if you will, when we want it. So if you think about certain types of batteries, so there's alkaline batteries, things that you know, Duracell, Energizer, whatever, you happen to use, all kinds of different ones out there. A lot of those alkaline batteries are just zinc reacting with manganese oxide to form zinc oxide and manganese dioxide. The thing about these, and so the manganese oxide here on the reactant side is positive 4 oxidation state. The zinc is a 0. On the other side, zinc is a +2, and the manganese is a +3 for each manganese. So there's a total of, in this case, 2 electrons in that redox reaction. But the whole thing is you have a setup such that so in this case, the zinc itself, right? The zinc is the anode, okay? And so the anode, if you will, is the can, and inside the can you'd have extra zinc to it so that your reaction could proceed until the chemical reaction finished, basically until your manganese oxide was used up. The manganese 4 oxide was used up. And so the way, and then on the inside of this, you'd have the other reactants in here as well. And so the way that this works is you have this chemical reaction that's ready to go, and it doesn't actually start to proceed until you connect, right? The wires there, right? And so essentially what we do when we use that electrical energy, we go up and we connect. We put in this wire here, right? That's the wire that we put in when we use a battery, is we allow those 2 half cells to be connected, thus allowing the transfer of electrons. And we harness that by running it through a little motor or something like that. That's the whole idea behind it. Now, there's a number of different types of chemical reactions. So the first one that we looked at was the alkaline. There are these zinc or these mercury button batteries, things that you generally put in very small devices. So zinc and mercury oxide react to form zinc oxide and mercury, right? That's one of the reasons why you want to make sure that you never just throw these away, is many times, depending upon the type of battery, like the zinc and manganese is not quite as important, but definitely if you have mercury in a battery, you don't want to just throw that into a landfill. It's much better to get it recycled so we aren't, depositing really nasty materials into landfills to poison people later, right? So this one is just zinc 2+ being formed. And then also, if you look at this, right, this is going to give you mercury metal. So your mercury here is mercury 2+, right? So the mercury is getting reduced, the zinc is getting oxidized. If you have a lithium ion battery, and there's a lot of different forms or ways the lithium ion battery can be set up, right? You have lithium as an ion attached to some sort of a carbon material. So the carbon C6, it's a substance that, so basically the lithium itself is interspersed within this carbon medium. You have some sort of so that lithium, we'll put it this way, the cobalt here, right, is going to change its oxidation state, and then what that is actually getting more oxidized here is the carbon. The C6 is the thing that gets oxidized, because the C6 goes from -1 overall for the 6 carbons all the way over here to 0, right? Whereas the cobalt is going from +4 over to here, where it's a +3 in that chemical reaction. Okay, and so there's just a lot of energy that can be stored, and the energy that's stored here is dependent upon the chemical reaction that's taking place. So the chemical reaction that takes place in a lithium ion battery allows you to store a lot of energy in a relatively small battery. So the materials make a big difference. The reactants and products make a big difference here. And we'll actually do a calculation in a minute about that, okay? Another type of, well, not a battery, but a fuel source is a fuel cell. So a fuel cell, for example, if you put in hydrogen gas and oxygen gas, you have a chemical reaction that occurs. And the chemical reaction that occurs is you're taking the hydrogen, okay, and you're causing that hydrogen to get oxidized. So it's going to go from 0 in the grand scheme of things to +1, okay. And you're taking oxygen and you're causing that oxygen to get reduced. So it's going to go from oxygen that's neutral to oxygen with 2- charge. Now, the way this works is that you're not burning it, you're doing it electrochemically. So you're causing the hydrogen to come in, the hydrogen hits an anode or flows through an anode compartment, and the electrons flow around through the wire, through, say, a light bulb or whatever you're trying to power, and over to the other side, where the electrons are then given to the oxygen as it comes through. The hydrogen tends to move from one side to the other, where it runs into oxygen and forms water, and then water is ejected on the other side, right? And so that's the idea of a fuel cell. You're really doing, if it were just burning of hydrogen, you'd probably lose a lot of the energy there just due to heat, because you're burning it. In this case, you're taking all of the energy and you're trying to move that energy into a flow of electrons, and you hope that not much or very, the minimal amount of heat is lost, so that you have high efficiency where the movement of the electrons is the thing that you're getting to happen most, so you can harness more of that energy. That's the idea behind a fuel cell. It's basically, rather than a combustion reaction, you're doing an electrochemical controlled reaction. There's still redox reactions, whether you're burning it or whether you're doing it in a fuel cell. It's just the idea is you're much more controlled and utilizing the energy in a much more efficient way for what we need. And so if we think about chemical reactions, there are a lot of chemical reactions out there. One of the types of batteries that has been used in the past for example, in cars is a lead acid battery, okay? So the lead acid battery has the chemical reaction as shown here. You have lead solid and lead oxide in a solution reacting with an acid. And so most cases, the acid that was used, I think almost all cases, was sulfuric acid. And now when you think about sulfuric acid, so sulfuric acid for every H2SO4, based on what we know about strong acids, right, we know that that's going to dissociate first and foremost into H plus aqueous plus HSO4 minus aqueous as well. And so we know that that's the first reaction. The second proton to come off happens at a much smaller dissociation, because HSO4 minus is a weak acid, whereas H2SO4 is a strong acid. So this chemical reaction overall is showing the sulfuric acid is already dissociated. Okay. And that reaction occurs such that you make lead sulfate, right, which is a solid, and water. Okay. And so the way you would charge a lead acid battery is you would force it in the reverse. You would apply a power source, right? And when you force that back to make the lead and the acid, then you actually recharge your battery. And so that's the whole idea behind recharging it. You force it back in the opposite direction by applying a power source to it to move the electrons and move the compounds back. And these types of batteries are generally relatively rechargeable. Now, not all chemical reactions in batteries are rechargeable. If you look back at, say, well, a fuel cell, you don't really recharge it so much as you refill it with hydrogen and oxygen. With an alkaline battery, that's not a very good rechargeable system. And that's basically because of the products that you make are harder to convert back in the other direction. Some batteries, however, are much more rechargeable. So nickel cadmium batteries, also called NiCads, if you've ever used like a screw gun or a battery powered tool, those are usually NiCad batteries or nickel cadmium batteries, and those ones will tend to be very rechargeable. You can use those many times. Now, it's not perfect, they do degrade after time, but overall, as long as you treat them properly, they can recharge well. And that's just causing, you force the reaction in the reverse by applying a power source. So if you take a lead acid battery with a 4.5 molar concentration of the acid, well, what this means is if you have 4.5 molar sulfuric acid, based on the fact that this essentially dissociates 100%, you can say that that's 4.5 molar and that's 4.5 molar. Right, for both the hydronium ion and the hydrogen sulfate ion. And so if you're actually looking at this, for the chemical reaction up top, right, the Q expression, okay, so the Q expression for that would just be, well, you notice we have solids and liquids, we're still using the same Q. So the Q for this is really 1 over the concentration of H plus squared times the concentration of HSO4 minus squared. Okay, so same idea with Qs. We're just applying things that we've done in the past in terms of equilibria. And that's the main key to this. Now, one other thing here is that I'm just going to give you so we can plug it in rather than go in and pull this stuff out of a table where sometimes these can be somewhat more complicated to find with some of these chemical reactions. So I'm just going to give you the E naught, okay, for this cell. Okay, so that would be the cathode's standard reduction potential minus the anode standard reduction potential. E naught for that cell is 2.04 volts. Okay, and so this type of reaction is similar to what we did with the concentration cell of zinc, only in this case it's a slightly different setup because the products and reactants are different. And so it's not just based on the concentrations, it's also based on the standard reduction potential of the cell. So the E naught for the cell will equal, the E for the cell, not the E naught for the cell. The E for the cell will equal E naught for the cell minus 0.0591 over N. And in this case, what we can see here is, so what's really being oxidized and being reduced, if you look at the lead here, the lead as lead oxide is +4. The lead as lead sulfide is 0, and all of it is winding up as +2. And so you can say, well, this lead, right, is being reduced, whereas this lead is being oxidized. And the total number of electrons involved in this is 2 electrons. So 0.0591 over 2 times the log of 1 over 4.5 squared times 4.5 squared. Right, because we just plug in the molarity of the hydrogen ions and the molarity of the hydrogen sulfide. And so for this, your E cell is 2.04 volts. And so what you wind up with, so your E cell will equal 2.04 volts minus negative, if you just plug through all of this math, negative 0.077 volts. So you're adding you're adding to your voltage here a small amount. And so your overall cell potential for a lead acid battery that has a 4.5 molar H2SO4 solution would be 2.117 volts. Okay, so again, this is just another electrochemical cell. This just happens to be one that we've used in cars for a long, long time. Okay. The next thing in here, so that's a lot of the calculations there for the cell potentials. Another thing that's important in redox chemistry is corrosion. So corrosion is just the process like rust, where something oxidizes, right? We think about its corrosion as being the slow oxidation of a metal. And this is a multi-billion-dollar industry every year because things rust and we have to replace them. And so the rusting process is where you have iron that gets oxidized. Eventually, the iron actually winds up as iron 3+ through really a sequence of chemical reactions. And depending upon where you go, the sequence can be written down in slightly different ways. I think we're still looking at the mechanism to some degree on this, but suffice to say that you really need the oxygen is the key here. The oxygen is doing the oxidation, right? It's the oxidizing agent, and your iron is what's getting oxidized. And so it does so in a very, very slow reaction, okay, where we make this iron oxide. And so this very slow reaction occurs when you have that water that's, it occurs in water with the oxygen present, and it does so in a way that corrodes things. And certain things that get corroded, like, I would always get in trouble when I was a kid leaving tools out in the yard. The shovel would rust, I would get yelled at, have to clean it up and all that. But it would make things that are metal more brittle because rust is brittle compared to the iron metal that is much more ductile. And in the maritime industry, it's a huge, huge issue because if you have your boat rusting, and your boat eventually rusts so badly it gets a hole, then you've got some major issues. So rust prevention becomes a problem, and we can look at rust prevention from an electrochemical standpoint. If you look at the important part of rusting, right? You're looking at iron going to form iron 2+. Now, if we think about the standard reduction potential of iron forming iron 2+, really it's the reduction potential would be Fe2+ plus 2 electrons, right, reacting to form iron solid, right? That's our reduction potential we're looking at. Well, we can actually prevent this by using what's called a sacrificial anode, okay? A sacrificial anode is basically you slap a piece of zinc onto a piece of iron. And what happens is if you actually look at the zinc, right, notice the zinc if you look at the reduction potential of zinc, right, zinc 2 plus 2 electrons going to form zinc solid, okay? So this, if you look at those reduction potentials, right, iron has a much larger reduction potential, right? And so if you have the zinc attached to the iron, right, the zinc is more likely to be oxidized. Okay, so the zinc is more likely to be oxidized. So if you put little and attach pieces of zinc metal to the hull of a, say, a warship or a container ship, what's going to happen is, and you want, of course, you want that container ship to be painted so that water doesn't get to the actual iron, but, you know, paint flakes off, right? And so the water in the ocean, right, where there's oxygen in the ocean also, rust can occur. But if you have these zinc pieces, essentially the metal of the hull of the ship will now act as a wire and transport the electrons from the rust to these pieces of zinc metal. Thus, what happens is that zinc metal will dissolve and the iron will remain intact because the zinc preferentially gets oxidized there, as opposed to having the iron rust, the hull become brittle, and eventually your ship sinks, okay? And it's not just in the maritime industry. Another place where you'll see galvanized metals, galvanized wire, for example, if you've ever seen a fence, right? A chain link fence has that gray tint to it because galvanization is a process in which electroplating is done to the metal to coat it in zinc so that over the course of time, the oxygen in the air that would otherwise react with an iron fence will then react with the zinc and it'll stay intact for much longer, staying stronger for a longer amount of time. So galvanization is a way of doing that. And things like screws and, you know, building materials, nails, wires that are out there exposed to the elements often are galvanized so that they don't rust, so that the zinc dissolves first, that the zinc reacts first. Now that means, that's one of the reasons why you see in old wire fences that were galvanized eventually that zinc does get used up and rinses away, say when it rains. And so eventually it goes away and you have to replace it, but it makes things last a significantly longer amount of time. So that's a really important and money-saving process. And then finally, the last bit of this is actually kind of what's the most useful, and we're going to spend the least amount of time because the only way that, so this process of electrolysis differs from other processes that are done is that that we've talked about galvanic cells primarily. In a galvanic cell, right, we have a spontaneous reaction that is allowing us to do some sort of electrochemical work. In an electrolytic cell, it's the opposite. You have a power source that forces a chemical reaction to occur such that the cell is going to go in the opposite direction. And that power source, some battery, or we're hooked up in, to an outlet or something like that, and we utilize the power source to force the electrons in the other direction. And so that's the whole idea. We're just, in this case, we're using electrical work to do chemical work, right? So we're using electricity to do chemical work or a chemical process, right? Chemical reaction. Okay, so how do we do that? Well, we hook up this power source and we force the electrons to flow. Okay, and we force the electrons to flow in such a way that there's a current being forced through the wire, and the current just measures the charge, right, being forced through that wire per amount of time. And that's measured in an amp or an ampere. And so 1 amp is 1 coulomb per second, okay? So that's what 1 amp is. And so we can use that to do, we can apply this, voltage or apply this potential to force the electrons in the other direction. When we force those electrons in the other direction, that's when we do chemistry. And the chemistry that we do is dependent upon how long do you force those electrons and at what current do you force those electrons? Because the current is going to be, well, look at it this way. If you apply a current for a certain amount of time, right? So current, which is in amps, times time, your units cancel. So your time units and seconds cancel. And so you're going to figure out the total charge. And the total charge is related, of course, to the number of electrons or moles of electrons through Faraday's constant. And so you can figure out how many moles of a product you can make based on the current and the time and the number of electrons at play in a chemical reaction. And that's the next example we're going to do. And that is just using a power source to do something useful. So in our example, we're going to apply a 12 amp current for 1 minute to a plate of to plate out silver onto a fork. So basically you're going to coat a fork with silver. And so you do that, you'd hook up a little electrode to the fork, you'd stick the fork into a solution of like silver nitrate or something like that, ionic silver, and you'd force electrons onto the fork to reduce that silver to silver metal. And so the number of electrons will determine how much silver plates out. And so if we have a 12 amp current, and we know that 12 amp current, we know that 1 amp is equal to 1 coulomb per second, then we can figure out the first thing, how many moles of electrons are used in this process. And then based on the moles of electrons, we can figure out how much silver plates out based on our understanding that silver is silver plus 1. It would be in solution plus an electron reacting to form silver solid. Okay, that's the idea behind this. And so it'd be really simple. You know that you have in 1 minute is 60 seconds, right? And so if you have 12 amps, 12.0 amps times 60 seconds gives you 720 coulombs, right? That would be your total charge. Okay. To find the moles of electrons, we just take that 720 coulombs and divide by Faraday's constant, which is 96,485 coulombs per mole of electrons. And so that tells you how many moles of electrons are transferred. So 7.46 times 10 to the third moles of electrons. And then from that, and knowing the mole ratio, that 1 electron will give us so 1 mole of electrons will give us 1 mole of silver solid, right? So that's our mole ratio. We can use that and the number of moles of electrons in order to determine the mass of silver, as long as we know the molar mass of silver. So you take your 7.46 times 10 to the third moles of electrons. You know you have 1 mole of electrons for every 1 mole of silver. And so our units get into moles of silver, and then you can just multiply by the molar mass. 107.9 grams of silver per mole of silver. And you wind up with, in this case, 0.805 grams of silver metal. And so this is useful work, right? This is something you can do if you're making, silver plated utensils, right? And understanding not just that, but how long it takes to get the thickness of the silver that you want on that plate or fork or whatever utensil is important for the grand scheme of making sure you're saving money as you're doing it. So you don't put too much on, but don't put too little that it rubs off too quickly. Okay. The other thing that's really important for you to think about is, well, where is this in society? And one of those things in society where electrolysis is really important is the production of fuel, because fuel is something, unlike a lot of the electricity that we produce, a fuel is another way of storing energy in chemical reactions similar to what a battery does. But a fuel is nice and easy to transport, right? Gasoline, you put it in your car, you fill up your car, you refill it really easily. Not as easy to change out a battery in a lot of cases, although we're working on it. We're getting better with technologies. But if we want to be really good at this, one of the things to solve a lot of our problems in the field of energy is taking and splitting water. There's been a lot of work done on this by a lot of people. I've actually got 2 YouTube links down here at the bottom for you to take a look at. And I'll let you take a look at those at your leisure. A guy from who's been at MIT and Harvard named Dan Nocera, his group has been working on a catalyst, and the catalyst is sort of the size of a small, like a credit card, could be bigger, but you put that into a glass of water. If you shine light on it, this catalyst lowers the activation energy for this to such a point that the sunlight provides enough energy to drive the reaction in the reverse. And if you were to collect the hydrogen and oxygen from the hydrolysis of water, you could then use that hydrogen and oxygen, say, in a fuel cell to then generate electricity that you need. And so there are 2 links there to some little videos that you may want to check out at your leisure, right? And that sort of touches a little bit on energy policy and potentially new things that might be coming about in, you know, some point in the future. All right. And so with that leads us to the end of chapter, where am I at?